A classical paradox about cutting and reassembling shapes into other shapes with a higher or lower measure. A total probability of 100% emerging from points with probability 0%. An infinitely tall spike that is infinitely thin integrating to 1. Different types of intervals. Those that tile seamlessly, those that leave gaps, and those that overlap, all with the same measure. And the Vitali set, a notorious set that isn't measurable, at least Lebesgue measurable. What I'm working on has to do with all of these, and with choices that have consequences. In this video, everything is about this choice. What measure does a point have? If you'll stick with me, you'll see that today I'll prove exactly none of that established math wrong. There'll be no metaphysical interpretation of the Banach-Tarski paradox in this video either. But I do hope that we'll be able to learn a lot from these issues. Given the nature of this video, an honest disclaimer is in order. I sell no NFTs, have no Patreon, and while I certainly would like a better job, this isn't primarily for making that happen either. Consider me a self-taught independent researcher and consider this video fresh off the press and not validated yet. Though I certainly would like to go through the motions one day. Consider this video primarily for the purposes of fun, learning, inspiration, and utility. There are reinvented wheels in this video, and there is also some non-standard notation ahead. Likewise, a few errors are quite likely, even if I have tried my best. Now then, let's add one more issue to the pile. The reason that I went looking for new tools. In graph coloring, which for once I will not be diving deeply into in this video, there exists the independence bound. Analyzing it step by step can help us find a value we want to know, the chromatic number. When using Lebesgue area and considering the ratio between a single point and a circle around it, the ratio of their measures is 0/0. Let's see where my battle with this issue has led me. This video will be rather long, and even so it will feel rushed in some sections since I have a submission deadline to meet, and putting out a video is better than putting out no video. I'll open by showing you the initial breakthrough, probabilistic cuts, which have made me start developing the titular tool of this video, Quantigrade, as well as some mistakes I made and epiphanies I had. Then, to respect your time, I will get into the substance of Quantigrade first. Finally, there will be a number of worked examples. If you've watched my previous video, which was also a Summer of Math exposition video, you've seen this. And I can already call it a naive mistake. For a measure, we care a lot about refinement invariance, meaning that if we cut any measured set into pieces, we want the measures of these individual pieces to sum together to the measure of the original set. For reasons you will see, I will be mostly using half-open intervals in this video, and the measure values I will assign to these sets will be Hahn series. If that doesn't tell you much, think of them like polynomials, but not as functions. Let's talk about the values that we could assign as a measure to half-open unit intervals. We have to decide two things. First, we need to decide how to deal with the boundary points. If we want to preserve refinement invariance, our choice is forced and we want half-open intervals to have monomial measure. Second, we need to decide the scale. Do we give the unit interval the measure 1? Or, since there are infinitely points in it, do we assign an infinite number to it? Usually the former is chosen. I will choose the latter, and we will be replacing omega with a different number later too. Let's actually cut an interval at a point. Now what? What state is the point in? Do we give it a membership probability? I've been very caught up with simply choosing to put the point in the left or right interval. After all, what is half a point? And yet, half a point is exactly what we need to deal with. a lot to really figure out how to get refinement and variance in Quantigrade and also to translate from Lebesgue to Quantigrade. Consider this interval. We expect 1 point included and 1 point excluded for a clean monomial measure. But that means we have a sort of boundary expectation, BE, and that is 50% for each endpoint. We could think of siphoning that probability from one side to another to get a deterministic state collapse. This translates to 2 dimensions, and arbitrarily more too, and this really is what sent me down the rabbit hole for good. Instead of constructing a square from scratch, consider cutting it out of an infinite plane. What do we do with the boundary points? We give them probabilities according to their internal angle. 25% for the corners, 50% for the side. Let's siphon the probabilities here, and we get a clean deterministic collapse. In 2D, the side expectation and the corner expectation create a combined boundary expectation, and for a square of side length x, this boundary expectation is 2x minus 1, a Hahn series, or polynomial. As a side note, I have proper formulas for the suspected boundary expectations and quantigrades of various shapes. However, I haven't gotten to fully test and verify them for myself even, so I can't give them more than an honorable mention for now. Really, this section deserves a video of its own, and it might get one, but for now let this marinate. Now, to tie this back to the intro, these tiles seamlessly tile the plane, just like half-open intervals do for a line. Now for a final, simpler sanity check on refinement and variance for the one-dimensional case. As you can see, if we cut the interval into increasingly smaller pieces, like this, we can count boundary points while our measure still remains refinement invariant. And that's it for the inspiration part. Next we'll have to start to actually build this from the ground up, with more rigor than we've used so far. We've learned a few things that we need to pay attention to in order to build our measure. If the values are a Hahn series, then we need a supporting number system. We could use omega or a non-specific hyperinteger, but I have slightly different plans. Let's make a precursor measure and see how far we'll get and when we are going to run into trouble. Let's make those numbers with a generator cascade. Coming up with names for these numbers has been more than a small hassle, but who knows how I even myself feel about this notation in the future. But for now, here they are. Alpha qua, beta qua, and gamma qua. And an infinite cascade beyond those, though we won't be dealing with them much. Now, especially for people that know their way around cardinal arithmetic, these are not infinite ZFC cardinals. They are numbers. Beta qua plus 1 is larger than beta qua. 2 times beta qua is larger than beta qua. Beta qua plus 1 equaling beta qua is never going to be a thing in the way that aleph naught plus 1 equals aleph naught as a thing. Let's build the quantigrade numbers. The construction is not unlike the surreal numbers, so the full range of these numbers are called the quantigrade surreals. These are all Hahn series numbers you can build from these generators, with the one small caveat that beta qua numbers can only have rational exponents. This is a field. If we deplete these numbers to get the quantigrade reals, we take away all the infinitesimal values. That means no infinite generators with negative exponents are considered quantigrade reals. If we deplete them further, we get the quantigrade rationals, meaning that the finite part of our quantigrade number, if it exists, must be an ordinary rational number. Another depletion step further is the next really important set of quantigrade numbers, the quantigrade integers. These are very important to understand. Every quantigrade number that has no infinitesimal and a finite part that is an element of the ordinary integers is considered a quantigrade integer. I'd advise taking a close look at the examples I'll show in a moment. Last, we have the quantigrade naturals, which are simply the positive quantigrade integers. Here are some examples. Gamma qua plus 3 is a quantigrade natural, but Square root of 2 times beta qua is also a quantigrade natural. Note that exponents as well as coefficients on infinite generators do not decide what type of number a quantigrade number is. Next, we have minus gamma qua as a quantigrade integer. Then we have beta qua plus 1/2. This is a quantigrade rational, because the finite part of this number is a rational. Then we have gamma qua plus the square root of 2. This is a quantigrade real, because the finite part is an irrational number. And finally, we have beta qua divided by gamma qua. This is an infinitesimal, and as such is considered a quantigrade serial. Now we have our number system, and we also have our precursor assumption. And we have an idea of how to get Lebesgue measure from this. This is reminiscent of non-standard analysis, but you have seen no ultrafilters here, and ultrafilters also will not be appearing in the entire rest of this video. The Vitali set is defined via an equivalence relation. Specifically, we will consider two different points to be in the same bin if their difference is a rational number. If the difference is not a rational number, we will consider them part of different bins. The union of all of these bins will be exactly all of the points that we initially considered. The Vitali set then uses the axiom of choice to pick exactly one point from each bin. The Vitali set may be diffuse, but if we take countable copies of it, translated by rational values, we can regain the entire original interval and more. Technically, we should be getting exactly twice as many points. But for this to work, the Vitali set needs to have a measure that is greater than 0. But we have infinitely many such sets to recover our initial interval, so the sum would be infinite. If the Vitali set has measure 0, we can't satisfy this inequality. Hence, the Vitali set is considered to be non-measurable. So, let's just force a size and see what happens. Let's define the measure for all reals in the unit interval as gamma qua. And let's also define the measure for all rationals in the unit interval as beta qua. Now we can resolve the arithmetic that previously was so daunting. The number of classes, that is the number of bins that we now have, is gamma qua over beta qua, which is also going to be the same as the measure of the Vitali set. Note here that I'm also introducing the grade. We will be talking about this a lot more later, so for now just take note that the grade of this Vitali set, if it were measurable, would be gamma qua minus beta qua. Let's check out that initial inequality again. If we define our measure as such, then the rationals in this larger interval would be 2 beta qua. And if we multiply 2 beta qua with gamma qua divided by beta qua, we get 2 gamma qua. The previous inequality then would translate as such that we have gamma qua smaller or equal to 2 gamma qua, smaller or equal to 3 gamma qua, and this is indeed true. We can now satisfy this inequality. So we have a temporary resolution. The Vitali set size is gamma qua divided by beta qua. But what was the cost of this? We are going to face multiple cracks in our measure now. If we roll with what we have previously defined, then the implication of this would be that the average gap between rational numbers would be the infinitesimal beta qua with a negative power of 1. This is not good, because we can count our way up these infinitesimals and never reach another rational. Now, you might think that we've introduced this problem just a moment ago, so the takeaway would be to just not do that. However, the same problem we are facing with the beta qua number is a problem we also face with the gamma qua number. This spacing that we imposed on beta qua and the rational numbers was never there, but it's also not there for gamma qua and the real numbers. And this aside, we also break the neat interval rule. If we make the measure work like this, we face this factor of gamma qua. The unit interval from 0 to 1 has the measure gamma qua. One final note. One Fiat is going to lock all of our generators, and as such we should deal with all of these problems right now. We are going to let go of the Vitali set as a measurable set. And we will also reacquire our neat interval rule the same way that Lebesgue measure has it. If we do it like this, you'll see that things will turn out much better for us. Let's move away from the real numbers even more. We're now not using the real numbers anymore for our measure values. Let's stop using them as our space too. Let's look at the Quantigrade integer lattice, and let's embed the real numbers in this lattice. Let's look at the finite values around the origin first. Since we want to map the real numbers to the gamma qua numbers, the only real number that would be embedded in this scale here actually is 0. Let's move up the scale. There is still only one point embedded in this space from our original space. Now that we're actually at the scale of gamma qua numbers, we can compare these two measure systems. The scale between them is exactly gamma qua. And if we embed the unit interval from the Lebesgue world, it turns into a very sparse subset in the Quantigrade world, but we fill this set out accordingly. We then can also lift sets that have different boundaries. In this case, if we lift the set from 0 to 1 with both boundary points included, this set gets now a different Quantigrade number. It gets the Quantigrade number gamma qua plus 1. Let's play around a little bit in this space. Consider this square. This square contains gamma qua to the power of 2 points. In the Quantigrade lattice, we can smear this set out into a single long thin line. But once we're at this scale, the original real number space is now nothing more than a sparse speck around the origin. The lattice continues far beyond where the real numbers end. We can use the property that we've seen at the end of the last chapter to consider measurability in the Quantigrade world like this. A set is measurable if its probability mass can be rearranged into a continuous set of the form 0 to m with one of the points included, for m being an element of the positive Quantigrade serials. But if you remember, the Quantigrade serials also contain infinitesimals. So let's talk about how we can measure things in Quantigrade theory. The simplest case is that we simply count points on a lattice. However, since Quantigrade is a hyperfinite counting measure, we can also count objects. Let's get a little more specific. We can also count points, but weigh them by probability. And there will actually be an application for this later in this video. If we're willing to deal with more complexity, we can view the Quantigrade lattice as filled with incompressible atoms, each with a measure of 100%. Now, not unlike for the real space, we can take parts of these atoms. Nothing is stopping us from deforming the atoms either. We could use capacity-constrained Voronoi tessellation to give each atom its own unique shape. And even beyond that, if you can construct it and if you can build a counting for it, you can make and measure it. I've teased grades earlier. In Quantigrade, grades are dimensions. All finite sets have a grade of 0. The sets that are equivalent to length sets in the Lebesgue perspective have a grade of gamma qua. A grade of gamma qua would be equal to 1d. A grade of gamma qua squared would be equal to 2d. However, in Quantigrade, even lines can have this grade. The grade is given by the biggest number in the Hahn series. So, a set with the measure gamma qua cubed plus beta qua minus 1 would have a grade of 3 gamma qua. Let's try to visualize this grade space, or at least the 2D variant of it. The vertical axis is our beta qua contribution to the grade. Note that these coefficients have to be rational values, in the same way that the measures can only have rational exponents for beta qua values. Let's have a look at some example values, and then we are going to reorder this entire space. Since the grades, exactly like the measures, can be Lex ordered, we can twist this entire space into a single column. Let's talk about realms and values. Here is the earlier power set relation visualized. If we have a binary tree of height beta qua, then this tree has gamma qua leaves. I'll also put the generalized formula that I've figured out on screen. I use the term realm to refer to collections of values with a specific highest value. The alpha realm then are all values which are finite. The beta realm are all the values where the highest generator, exponents excluded, is some form of beta qua, and likewise for the gamma realm. Note the ability to jump from one realm to the next via power sets, but just as there is no way to reach countable infinity in ZSC with power sets on finite sets, there is no way to do that here either. Let's have a look at product measures. In Quantigrade, these could hardly be simpler. For any two valid Quantigrade sets, multiplying them is trivial and always possible. Here is a visualization of what it would look like to halve and compress a closed lifted unit interval. Lebesgue is the quick credit. The real line is ready-made, the machinery is familiar, and almost everywhere is almost always enough. The interest comes later in non-measurable sets, boundary ambiguity, and the places where almost everywhere quietly means that we have agreed not to look too closely. It just so happens that for the infinite combinatorics that I can't leave alone, this isn't cutting it. Quantigrade asks for an upfront investment. A new number system, explicit boundary choices, and a habit of asking what a point even really is. In return, the paradoxes lose the bite I can't afford when I want to perform a deep breakdown of infinite graphs. Lebesgue won't let me apply old tools like the independence bound to infinite graphs with a new coat of paint. Even the precursor to the Quantigrade precursor, the very first inklings of this, which I call transdimensional measure, let me do this successfully. I don't want to oversell this. For most of mathematics, Lebesgue is simply the better trade. Quantigrade is for problems where the exceptions, the boundaries, and the exact cardinality are not noise but the actual subject of the question. The bet is that this way you can see and analyze the information you would otherwise have to ignore. I have a number of conjectures that require this tool. Every measure chooses a fiat. Quantigrade chooses explicitness. If you've watched this video this far, I would say there is definitely a non-zero chance that you've watched the Dartboard video by 3 Blue 1 Brown. Let's have a look at how simple things can actually get with Quantigrade. If we replace Qgħ with centimeters as an explicit area unit here, we can calculate the probability of hitting any single point on this dartboard. Assuming a genuinely random throw and a semi-random area of 2026 square centimeters, a uniform player is going to have a chance of hitting each point of simply the inverse of that, that is, 1 divided by 2026 square centimeters. And multiplying this by the original area gives us exactly 1, or 100% back. You can think of this as taking the dart throw as a single event, a single point, and then exploding its probability and associating an infinitesimal piece of that with each lattice point for the dartboard. Let's consider a slightly more trained player. They are not perfect, but they hit the bullseye considerably more often than the random thrower. But the arithmetic still stays simple. Take the bullseye, 1 square centimeter. If each atom in there gets a 1 in 20 per square centimeter chance, then the total chance of hitting the bullseye is 5%. The play zone is much larger, 2000 square centimeters. So even with a much smaller per atom chance, 9 over 20,000 per square centimeter, it still collects 90%. And finally, the failure run. 25 square centimeters with 1 over 500 per square centimeter. That's another 5%, same chance as the bullseye. Added up, 100% chance every possible outcome was accounted for. Every atom got a positive exact probability, even if infinitesimal. I should be honest, the Dirac delta wasn't my idea. As much as I'd like to do a full AI usage disclosure time one permitted, so the long and short of it is, I'm using current AI systems as assistants, but none of the Quantigrade design actually comes from AI. With that said, Claude, when I still used it that is, suggested to look into the Dirac delta in this context. Wasn't sure why that would be relevant, but I did my homework and here we are. Here's the Heaviside step function on our lattice. It jumps by Qgħ. Take the backward difference. Almost everywhere it's 0. Exactly at 0 it's Qgħ. That's also the delta. Just a mundane function. The integral, Qgħ. Or in general, every impulse function can have a height and integral that are trivially the same. There definitely is more value in talking about this, I think, and I might sometime, but I fear that day is not today. Let's count a linear function, and with it we have one quick warning. This linear function is a mundane function in Quantigrade, which is Qgħx, which, yes, has derivative Qgħ everywhere. Because sums will trick you, it might be tempting to just hand the same values from the well-behaved intervals into the sum. Center the atoms instead. Here's F2, built as a Cayley graph. This is the free group on 2 generators. Each point is a reduced word, meaning no letter followed by its inverse. These words give us rotations on a sphere, and a way to pick points and decompose the sphere into very fine sets. The first letter is the last rotation applied. From any node, you can add 3 new letters, anything except the inverse of the last one. So the tree branches 4 times at the first step, then 3 times forever. Consider this word. The first letter and last rotation is the inverse of A. So if we rotate by A, we get closer to the origin. Now take all words ending in A and assume the tree has infinite depth. Multiply on the right by A inverse. That just strips the final A. The word A collapses to the identity. Every other word shortens by 1 letter, but they are infinitely long. What do you get? The identity plus all words ending in A, B, or B inverse. Now, with a few more shenanigans, you can double a ball in 3 dimensions. I said I wouldn't disprove anything in this video, and indeed, this makes sense. It makes sense if you accept all the premises, that is. Here, let's look at the arithmetic for the finite case. I had to introduce address depth here, a real explicit number. Why? Now, let's take the same set but at a finite address depth and perform the decomposition again. This set has 13 points, and after we decompose it, it has still 13 points, just split differently. And this is where a hyperfinite counting measure would severely disagree with the classical view. The classical view requires us to grant completion at infinity. But the number of points in this tree triples every single word, and it never stops tripling. From the quantigrade perspective, or in general from the perspective of a hyperfinite counting measure, granting this infinite address depth is akin to setting 1 equals 3. Now, it's not as easy as just not doing that then. But if we use a hyperfinite counting measure, we can in fact track this address depth. In this perspective, every word has a last and a first letter. And every letter in the middle also has a successor and a predecessor. And here is where our power set arithmetic gives us a very pretty little formula. We can calculate the address depth it takes for a sphere with a surface area of gamma quar squared. And that address depth is roughly 1.26 beta quar, so actually uncountable infinity. And as such, my perspective on this paradox is that it's really largely combinatorial. If we demand an explicit hyperfinite depth, size is preserved. I'm also somewhat curious about how far I can push this, but I'm not sure if and when I will go back to this. I built all this really just for one purpose: attacking and analyzing infinite graphs. Using Quantigrade, there is no useless 0 over 0 for the ratio of a point to its neighbors. For a circle with radius gamma quar, that ratio is 2 pi gamma quar. Finally, the axiom of choice should, in this system, turn out much friendlier. Because the measure of sets is completely independent from their geometry, exploded colorings remain measurable. And that gives me a lot of questions I can ask about infinite graphs in Quantigrade that Lebesgue can't attempt to answer. If you actually made it this far, thanks, and I suppose also sorry. Clearly this video needed more time in the oven still, but this is everything I could manage from the very beginning of the SOMIS submission period all the way to the end. And now, I will focus on using this. After all, the proof is in the pudding. Let's see what we can bake.